Sorry. We'll see how it keeps up with the internet here. So this is known as an enolate. Okay, the ATE ending because it's an anion, right? But this stabilizes this interaction. This resonance stabilizes the enolate. So that's why we can make, that's why the alpha carbon is more acidic. And because it's acidic, the alpha carbon can act as a nucleophile. Okay, so the reaction that we did this last week in lab involved an enolate ion that acted as a nucleophile and attacked the aldehyde of benzaldehyde. And we'll hopefully get to that reaction this week.
So the CH2, I mean the CH acts as a nucleophile?
Yeah, so this carbon, this alpha carbon, right, can be nucleophilic. Yeah, let's see what else is there. Oh yeah, just side note, there's actually 2 nucleophilic sites on this one. Alpha carbon is a nucleophile. The oxygen can also be a nucleophile. Let's put it on the next line. So try to can also act as a nucleophile. But it's primarily nucleophilic with small ions like hydrogen. So hydrogens, maybe small metal ions, things like that. Nucleophile towards hydrogen. Anything else, like bigger than hydrogen, it's typically the carbon that acts as the nucleophile, okay? And that has a little bit, oops, sorry. That has a little bit to do with what we talked about at the end. I've mentioned at the end of the last chapter, there's like one paragraph on hard soft nucleophiles. It has to do with the hard soft nucleophile thing. You don't really need to like know that in detail, but hydrogen's a small ion, and oxygen, when it carries the negative charge, is also relatively small, and so they match in size, and so that's the reason that it tends to attach to that point. Okay. So we're going to look at acid strength of the alpha carbon. So pKa's again. So just for comparison purposes, some pKa values. If you take CH2 and then double bond CH, and we're looking at this particular hydrogen here, pKa is about 50. For alkanes, it's closer to 60, but it's pretty high because there is no good charge delocalization when you put the charge on that carbon. It's right on that sp2 hybridized carbon, though. So it can't participate with the double bond. It's not allylic. If we're looking at this, an alpha on a aldehyde or a ketone, okay? So ballpark numbers where R is alkyl, and we'll do some of the details like which is stronger, weaker in a little bit. or hydrogen. Okay. The pKa is around 16 to 20. So if you remember, like alcohols, sodium hydroxide, they're all around 15.5. If you put sodium hydroxide, like high concentration of sodium hydroxide in here, it will deprotonate that hydrogen. If you use stronger bases, you can deprotonate a larger percentage of it. Okay.
Is that 16 to 20?
16 to 20. Sorry, 16. The 15 is alcohols, things like that, sodium hydroxide. But it's in the same ballpark. So there's like when you put sodium hydroxide in with a ketone or an aldehyde, there's a fairly significant percentage of it that can be acting as a nucleophile, okay? Like 50% or more. Okay. Let's do a couple of others. I'm going to draw these side by side, actually, just 3 or 4 of them. Yeah, I'll go. I don't know how I want to do it. I'll just list them. So let's look at esters real quick, because this gives us some idea about what influences the pKa. Sorry. Like this. So here's an ester, and then I have a hydrogen here. So this is the hydrogen that I'm looking at. All right. So aldehydes, ketones, 15, 16. Esters are around 25. That's the pKa. So that's similar to like acetylenes, which are 25, right? So you can pull that hydrogen off using very strong bases. So why is this so much weaker than an aldehydes and ketones, like 10 orders of magnitude? What's that? Resonance. Yeah, because this oxygen can donate to this bond here, right? And you can get a double bond on the right. So there's still resonance stabilization on the alpha carbon, but because the oxygen is an electron donator, it can donate negative charge to this oxygen like this. And so that's what, if you're donating electron density from the oxygen, then you can't donate it from the enolate ion, and so as a result, it's not as stabilized. Okay. So what about this? Where would you expect this to be? Like that. Do you think pK is higher or lower?
Probably just higher or lower.
When you compare nitrogen and oxygen on the periodic table, what's the major difference in terms of like the two atoms? What are the major differences?
Oxygen more electronegative.
Yeah, and being more electronegative, it's not as good at donating electrons. So nitrogen's a better electron donator. So better electron donation, which means it competes more strongly with the enolate ion, which means it's going to be a weaker acid. So it drives the pKa up higher. These pKa's tend to be around 30. So basically, when you're trying to compare acid strengths for alpha carbons, you're looking at just a couple of different things. Really, you're just looking for, really, we're just looking for electron withdrawing groups, or electron donating groups, sorry. Let me spell it out. So I'll write it like this. Any substituent that competes for stabilization makes the alpha carbon less acidic. Okay, and then anything that stabilizes, right? Here's Sue in the back. Your mic's on, Sue. Any group that stabilizes the negative charge makes the alpha carbon more acidic. You know, that means lower pKa. So if you have a structure that looks like this, versus this, right? So I take, instead of having a CH3, I put a fluorine on there, right? The fluorine is good at stabilizing negative charge. It's an inductive effect. So the same stuff that we learned last semester, inductive effect. And so this particular acid would be stronger. Okay. So, but the other way that's real common in these reactions is to create what's called a beta die ketone. And a beta die ketone looks like simply like this. You take I'll draw an example of one. So this is a beta die ketone because they're beta carbons away, right? So from this position, this is alpha and then beta. Or if you go the other way, it's alpha and beta going the other way. So they're separated 3 carbons apart. So these beta die ketones tend to be much more acidic because now what you do is you take that pair of electrons that's on the enolate and you distribute it to 2 oxygens. So there's more resonance stabilization for that particular lone pair. pKa's on these guys tend to be around, this particular one's 8.9, but they tend to be in the low 8, 9 range. And stabilization, just to practice, because we don't do a lot of this anymore, I'm going to draw. If you take and you remove with the base the hydrogen, you get this enolate. And this can go by resonance either direction, right? So it can go to the, if it goes to the left, then you're going to get your enolate ion this way. Or you could go in the other direction. Oh, all my pens are the same color now. Well, that's not cool. Let's get a different color pen out. Or you could go in this direction like that. Okay, so either direction produces an enolate ion.
So where would the positive charge not have?
What's that?
The positive charge.
No positive charge.
The positive charge?
No. Well, the base might have a positive charge on it because it pulled the hydrogen off, but leave a negative charge behind. Yeah. So, give you another example. This one's a little bit more confusing to deal with. Did you see that more? You got it? Here's one that's a little bit more confusing to deal with. So I took the CH3 and I just replaced it with a hydrogen. And the pK for that is 5.9. So it's actually stronger by putting a hydrogen on there, which means it's the negative charge is even more stable on the enolate ion.
So there is both.
If they're both hydrogens, they're like it's in the low 4s.
Okay, so the more hydrogens, the less.
The more acidic it becomes, right? And the reason. So let me just make a little note here. Lower, right, means the enolate ion is more stable. And the reason is CH3 groups. Your favorite answer? Hyperconjugation. Donate electron density by hyperconjugation. Okay. So that whole thing, you know, making the negative charge more stable, if you put the hydrogen on it, there's not the hyperconjugation pushing negative charge into the enolate. And so that lets it be a little bit more stable. The 8.9?
Okay.
Yeah. Okay. Let's see. Yeah. I want to do something. Okay, let me show you this. I'll set it up like this. What does acetone look like?
C, double bond O,
And then CH3s on both sides?
Yeah.
Acetone. Acetone looks like this, right? So acetone is capable of forming an enolate ion. And when it forms an enolate ion, it does so sort of in this fashion. Let me make this a 2 and I'll draw the hydrogen off of it. It's a lot easier to draw enolate reactions if you don't draw CH3s, but you draw the hydrogens out. And if you have a base, okay, you can attack this, and then what ends up happening is you can form the enolate like this. Sorry, that's a single bond to the oxygen. Like that. Okay. Now, when you look at the equilibrium amounts, right, This is 99.9% of it. And this is 0.1%. Plus the reactions, unless you actually add a base, the process called tautomerization, that is the conversion of the keto to the enol form, that is this. I'm just drawing bond line form right now. This is the keto, this is the enol. That reaction rate is actually slow. So when you have acetone, and I'm going to probably ruin a whole lot last doing this. I'll go against the sodium hydroxide. Yeah. There's actually enolization going on in here, or keto-enol tautomerization going on in here. And here's the thing. If it was going on at any significant rate, it turns out this is a nucleophile, right? So we talked about before. The alpha carbon's a nucleophile, and it can attack a ketone. So it can actually go like this. I'll draw the mechanism over here. And then I'll tell you how I learned this happens the hard way. So I can have this, and this bond goes like this, and then this attacks that carbon and forms this compound. Like that? Oh yeah, let you guys get count up. And that's actually stable. Right back. Let it go. So I have to do this and I have to return this. I just stole it off somebody else's experiment card.
Catalyzing hydroxide.
Yeah, so it needs a base, right? We're going to catalyze this reaction with the base. So you have to remember, this reaction that I'm about to show you happens all the time.
Bottle or?
Yeah, it's going on in here, but the rate of reaction is really slow.
No, I cannot move that.
Ready to describe to Sue.
So let's try this.
Is this like a red reaction?
It's a base catalyzed reaction. I'm just put a little bit in. I don't need a lot, but I don't have a choice of that. Oh, it's going to happen right away or not?
Wow, you're a big one.
Yeah, might need a little bit more. It's not concentrated, that's fine. Well, come on, go, dude.
What's the like?
It's going to cloud up, it polymerizes. It doesn't form a solid polymer. It's relatively. You can kind of see it starting to start. Cloudiness is going on in there.
Yeah.
That's the last week.
Yeah, give it some time. But what's going on is that reaction that's right there. Eventually, it gets all cloudy. All right, I'll do the whole thing.
So is it just another reacting paper?
Yeah, but we can make the reaction fast, and when the reaction's fast enough, it'll that reaction will complete, and then it'll completely turn the bottle like it would paint. So apparently, you just have to have a much higher concentration than I had. You can see the cloudiness sort of starting. The way I found this out actually is students misusing acetone bottles. What students would do. And what they did was they took the acetone bottle and they were trying to wash something off. And they're going like this, and they had to squeeze, right? And what was in here was concentrated sodium hydroxide, and then they sucked it up back in the bottle. They sat on the shelf for a while, and we came back, it was all like cloudy. Like, what happened there?
What?
They actually were able to suck the sodium hydroxide back into the bottle.
Oh, so they had it in, they squeezed it and put it in a
Yeah.
solution.
Yeah, they stuck the tip all the way into the solution, and when they took it out, they just set it down, and then everybody comes back later, and all the acetone. And I'm like, what? It's actually not mixing, that's part of the problem. It might be that other base is mixed better, but there's actually a layer. I usually do it with sodium hydroxide, so maybe there's just enough solid.
What was just
solid
warm it up? This reaction.
Yeah, anyways, now I'm going to hide the other. I wasted a whole bunch.
Sodium and water.
And then I got to put this back before he recognizes that I used it. I don't have enough for that.
So you guys know what to do next time we work in the lab. So
Before it the acetone.
yeah, straight into the acetone.
So, but you know those bottles of acetone, they sit there forever and they stay clear. And within a few minutes, we can make it cloudy just by adding a little bit of a base to it. And the idea is that this tautomerization, this enolization, is catalyzed by a base, but it can also be catalyzed by an acid. So even though this is 0.1%, right, it can still be effective in a reaction as long as you can make it quickly. If you can make it quickly, then it'll react with whatever reagent you add to it. And if the product is more stable, you'll definitely get a lot of product out of it. Okay. This, by the way, this particular enol, let's see, or this particular, oh, sorry, different one. Let me draw this down here. Oh, actually, no, I'll draw, it's a different structure. The only enol that has significantly higher concentrations is this one. This enol has a concentration of about 15% at equilibrium. And it's mostly because of hydrogen bonding, yeah. So intramolecular hydrogen bonding. Okay, so a characteristic of beta die ketone. So. Okay, so catalyzing the tautomerization reaction. So acid catalyst. Of tautomerization. Goes like this. So I'll use acetone as the example. It's the easiest one. And then you have an acid. And the first step is picking up the proton, protonation. And then you end up with this. And then it turns out, right? When you protonate an oxygen on a carbonyl, it makes the carbonyl more electrophilic, and it also makes this hydrogen more acidic. So if you're doing this in water, for example, this can easily pick that up. And then you have the enol. And so in water, you would have hydronium, which would go back and act as the source of the hydrogen. One thing about the mechanism that's useful to point out is the same stuff that we did when we did the reactions of carboxylic acid derivatives under acid catalyst. There are no negative charges. Base catalysis can also take place. Okay. And then we, again, using acetone as the example, but it could be any aldehyde or ketone. The base in an aqueous solution would be like sodium hydroxide. And then you get this species. So this is the enolate. So this is an enol. This is an enolate. And then in an aqueous solution, you do that, and this is your enol. I'll draw it out. That plus OH minus. Which is the catalyst for the reaction. So this last step where I show the hydronium, right? That I'm only showing that because it's a catalytic reaction. So you only have to, in principle, only have to get a little bit to dissolve in, and it works. Again, using the same sort of principles that we used in looking at carboxylic acid derivatives, right? No positive species. So to help you remember you're getting the mechanisms right, under acid catalyst, no negatives, only positives and neutrals, and then under base catalysis, it's only negatives or neutrals and no positives.
So the tautomerization is where it just goes automatically, right? After the form the product?
Yeah, so once you form this is just to show how it speeds it up, right? It's always kind of going on automatically, but adding an acid or base speeds it up by making that, for example, under acid catalysis, making the CH2 more able to pick up a negative charge because this becomes more electrophilic, right? And then down here, by taking the hydrogen off, it comes up to here, puts a negative charge. So the base speeds up this reaction by pulling this hydrogen off. So the first step gets sped up in both.
Okay.
Yeah.
Could you go back to the reaction between the enol and the ketones? Yeah, right there. How
Yeah.
do you get that to a neutral?
Oh, sorry. Yeah, there's a negative here, huh? Yeah.
Oh, yeah, it is.
Would that also form a hydrogen bond?
Yeah, actually, it's an acid. It'll be an acid-base reaction.
Oh, really?
Just pick it up.
Okay.
Yeah. I meant to draw that in and I forgot. Sorry.
Yeah, that's wondering.
Yeah, so you can pick that up and that forms that product. So that's in principle what we were making in that flask when I added the potassium hydroxide. It's interesting. I'll have to try it with sodium hydroxide. You know what the other thing is? That maybe the acetone here might be better than the acetone I had at City. Because you need a little bit of water to make it happen. So could possibly be that. All right. Okay, first reaction called halogenation. And you can kind of imagine why a halogenation reaction might be useful, because you make alkyl halides, which you can then do substitution or elimination or a bunch of other stuff. The basic reaction looks like this. The overall, I should say, reaction looks like this. I'll do it with an aldehyde, I guess. Then I don't have to worry about competing other side reactions for now. And this is going to be catalyzed either with acid or base. So I'm just going to say catalyst down here. We'll have to add that in. Well, I'll do the mechanism so you can see how it works out in the mechanism. And then you'll do this. Okay. So when you're doing acid catalysts, this is what you get for acid. If you use a base catalyst, you get a different product. It's related, and you'll see in just a second what it is, because I'll draw it. So when you have a base catalyst, that's the product that you get. So what ends up happening under basic conditions, both hydrogens, generally speaking, get replaced.
If they didn't use the catalyst?
Then it's just really slow, and it'll probably be the acid product. All right. So we'll do the base catalyst mechanism. Okie dokie. Let's see. R, C, H, A. Oh, actually, I'm going to draw both hydrogens because it's a base catalyzed one. And we're going to remove both of them at some point. So I'll just draw them both in. I'll use R's on the ends, but the R's could be hydrogens. They could be other things. And then I add a base. So that, let's say OH minus. And that's typically what we're going to be using. And that'll form this enolate. That. And then this is stabilized by resonance, right? And so typically what people will do is they'll draw the resonance form like this. And the reason that they're doing that is because the oxygen's more electronegative and it's most likely to hold a negative charge. It's like the more stable resonance contributor. So now you end up with this. And this is done with bromine present. Okay, so Br2. So I'll add that to the reaction arrow. But actually, you know what? I'll add it down here because it's a mechanism, Br2. When the enolate collapses, that is, it goes like this, all right, what it ends up doing is it ends up picking up a bromine. Bromine's polarizable, right? So it can attack and displace the bromine at the appropriate moment, and then you'll end up with this. So right now I have a monobrominated product. I've added one of the bromines to the product. Okay. What does the halogen do to the pKa of the hydrogen? Makes it more or less acidic? More, because it's an electron withdrawing group essentially, right? Polarizes that bond. And so anything you can do to stabilize makes it more acidic. So it ends up being more acidic than the original. And this is why you always end up adding 2 at this position, because it's more acidic and more readily deprotonates. And so now you can bring the OH in, another base, attack, and form another enolate. And so you're going to end up with this enolate ion. And this can pick up a second proton or second bromine. So even if you try to limit it by putting 1 equivalent in, the second one addition is faster than the first, and you'll end up with a lot of the both hydrogens substituted with bromines.
Yeah, good.
Yeah.
Does that enolate come from the resonance structure? You saving time for not drawing the
No.
negative charge of the minus?
This one?
Carbon?
This one comes from this.
Is that just one step? It's not a.
Yeah, it's just, it can be just one step. I was just saving time by not putting a pair of electrons, yeah. Yeah, so second bromine, Br. All right, pair of electrons goes back, double bond attacks the bromine, and then you end up with your di-substituted product.
So it wouldn't attack the double bond that's already floating around?
It could, actually, but the bromine's probably a lot less sterically hindered. It's probably faster. It's probably more polarizable too, but I don't know about that for sure. Yeah, so you end up with like this. What you will find out in doing these reactions is there's a lot of byproducts that can get made. A lot of things, other things going on.
So we need 2 equivalents?
Well, that's what I say. Even if you put 1 in, because the second deprotonation is faster than the first, you're still going to get that product, but then you'll get a mixture of other things too. So yeah, if you're going to do it right, you'll do 2 and you'll replace them all.
I have a question.
Yeah.
On the second step, why did we make the double bonds instead of just grabbing the bromine with the electrons?
Wait, are you talking about this
Second
step?
No,
This?
one up.
This?
Before the resonance.
Before that.
Yeah, right there.
Oh, why didn't I?
I know, it's one more thing.
Yeah.
Why didn't I do this?
Yeah, just grab.
Yeah, I just saved time. I just didn't do it. Right.
No, why don't you grab the bromine with the negative carbon electrons?
Oh, so this step is generally shown because this is the stable intermediate. So think about it like this. I have 2 resonance contributors, right? These are really the same structure. Does that make sense? Because they're just related to each other by resonance. I just shifted these electrons from here to here, right? Which one's better for holding the negative charge, the oxygen or the carbon? Yeah, so I drew it like this because the oxygen typically, like when it's in the intermediate form, is is the more stable contributor, and it represents the molecule better. But that's the only reason. I mean, you could have, like said, it goes like this, directly grabbing that, but it really looks like this more than it does look like this at the intermediate. Yeah, so that's the reasoning for drawing it like that. I'm trying to think of a good analogy of like when the things like that happen. But I don't have any, like I'm thinking about like a baseball player, you could show them with the bat, right? And you just show the ball flying in the field, they're like this, right? But really when they're hitting the ball, they're like this. I don't know. It's baseball season. And I spend a lot of time on the field. Okay. Under acidic conditions, by the way, the mechanism is basically this. Essentially, you guys got to get out of the habit of using the word basically. Is essentially the same. I don't think I have it in my notes, but I'll go ahead and draw it. So I have R, C, H. I'll draw it the same way I did the other one. I'll do acidic conditions. So under acidic conditions, we'll pick up a proton first. And then you end up doing this. These are all aqueous reactions, so the base in this case is water. So it can pick up the hydrogen, and it goes directly to this form.
Well, the only reason it doesn't go again is because it's at OH now.
Yeah, so yeah, that's what I was going to get to. So I get this, there's a hydrogen here. And then when the bromine comes along, the mechanism, yeah.
Is that the top right? Is that another case that you just not drawing right?
No, because under acidic conditions, because this is more electrophilic, it'll pull electrons directly. Right? It is true, though. It is true that this is the more stable form as well, right? Because, well, actually, no. This is the more stable form because,
Yeah.
what did I do? I redrew.
Because the H pulls away. H pulls the water pulls the hydrogen.
Yeah, because the C double bond O is a shorter bond. So then in the mechanism, we just follow along essentially the same pathway like that. It's good to call me on those because you just never quite know sometimes. You get this guy. And then this can be deprotonated by a water molecule. That. But here's the thing, even though this hydrogen's more acidic, there's not a strong base to pull it off. So it doesn't accelerate the second step in the reaction, the second addition. So typically this stops at the first addition, and then you end up with one bromine in that position because you don't have the OH minus to pull the hydrogen off to make it an enolate ion.
Would the other BR just pick up?
It's just going to be a Br minus.
So that would you pick up the protonated?
No, because Br minus is not as strongly as basic as H2O is. H2O is a better base. Like the protonated H2O pKa is like -2, but the protonated, like HBr is like -7 or 8. It's much more acidic. Okay. So I'm going to cover a couple more reactions and then I'll stop on this section. The first reaction is one of those useful reactions. It's what you can do with a, it's called a haloform reaction. And it's the reaction of a methyl ketone. So a methyl ketone is just one of these guys. And so acetone would be a methyl ketone as well. And under basic conditions, we'll do this. We'll have an excess of OH minus, or actually I2 and OH minus. And then what you end up with is this, carboxylic acid. Excess. It's X. Yeah. It's the element XS. Sorry. And then, so two things about this. It's a conversion of a methyl ketone to a carboxylic acid. It's also the test, the haloform reaction. When we use iodine, it's called the iodoform reaction. And it turns out the other product is this. Let's see, CHI3. It turns out CHI3 tends to precipitate out of the solution. It's like a yellowy solid, yellow, white. And back in the good old days, when we wanted to determine structures, the iodoform test was a common one to do. It's done in acetone, and it turns out not acetone. What's it called?
Is it CH3I?
Yeah, CHI3.
Okay.
So
where do the other hydrogens go?
Well, I'll draw the mechanism so you can see it. But this is iodoform. If you do it with like chlorine, like Cl2, you end up with chloroform. So iodoform is the general formula for iodoform, chloroform, all those is 3 of the halogens, 1 hydrogen on a carbon. Okay. Mechanism. Yeah. Okay, I'm going to abbreviate it a little bit because it's really repetitious. So I'll start with a methyl ketone here. And I'm going to just draw 1 of the hydrogens out. Okay. And it's done aqueous sodium hydroxide. So I have an OH minus. And it attacks the hydrogen and forms the enolate. Oh yeah, I'm just going to save time and draw it the other way. Just do it like this. So I get this guy. This is my enolate.
So that's just save time again?
Time saver. Yep.
Sure.
I figured you'd be okay with that.
I mean, I just want to know the mechanism exactly, because if we save time on the test.
Oh, yeah, no, this is okay on the test either way.
Sure.
But if I actually identify the enolate ion, right, it's either of those two. It's a resonance between those two structures. All right. So, yeah, anyways. Why did I take the methyl hydrogen instead of, like, on the R group? There's probably hydrogen there, right? I just didn't draw it. Because in the resonance.
Less therapeutic.
No, well, that's part of it. It's very accessible, but the main reason is that resonance form that I didn't draw that's driving coal nuts. The CH2 is more stable with the negative charge. That's why you pulled the terminal one off. If you do it internally, then you have a substituted carbon, and anions tend to be more stable on less substituted carbons. So the reason for taking this hydrogen is because it's more stable to be terminal. But the net effect then is, right, when this collapses, you're adding the iodine to the methyl group on the methyl ketone rather than internally. Okay. So now we're going to get this. And the reason we're using an excess is we're going to end up replacing all the hydrogens.
Just because I'm white.
Yeah, so that's what I'm saying. That's what I was thinking to myself. Do I want to draw them all out? I don't really want to draw them all out. Eventually, you'll get to this guy. Again, time-saving measures. The sodium hydroxide, right, is using up is pulling off these hydrogens here.
And then that becomes a good leading group.
Yeah, so now it's a good leading group. And so what ends up happening next in the reaction is you have OH minus. It's a tetrahedral intermediate, just like the first chapter of carboxylic acid derivatives. And we're going to end up with a carbon, O minus, how do I want to do this? You know what? I'll do it straight up. And I'll draw these down a little bit. Ci3, and then OH like that. And then this collapses. This, and then this breaks off and takes the electrons with it, and with the more polarizable iodines on there, you're able to sustain that charge as a leaving group. And then the next thing that happens, right, you have your carboxylic acid, right? So you have R, C, double bond O, O, and I'm going to draw the H out like this. You have the Ci3 minus, and it's just an acid-base reaction to the product. So you end up with a carboxylate, which then you can protonate with an acid and return back to the carboxylic acid. To the way of drawing it. And this is the iodoform. But you can convert methyl ketones into carboxylic acids this way. You can also use the iodoform reaction to identify methyl ketones. We don't do that very often anymore. Most of the stuff we do now for analysis is instrumental. You run it in a mass spectrometer and it tells you things like that. But this is an easy way to tell. Okay, so that was the first. Yeah, go ahead.
Does it always take off the hydrogen?
Yeah, because it's an acid and a base, right? Okay. It's in basic solution, so it could be like the sodium hydroxide takes the hydrogen off, but the net is the iodoform is strongly basic enough. Like if you have water, it'll pull a proton off of that. So the net is you form this carboxylic acid, and then the Ci3 minus picks up the hydrogen, either directly or indirectly somehow.
You just put make that negative oxygen afterwards then?
Yeah, so then at the end, like when to work this thing up to get the carboxylic acid out, you have to add an acid to it, neutralize it, and come out as carboxylic acid.
And you wouldn't have that acid in there from
This CH.
Not during the reaction, but you have to do it as a follow-up step to isolate it.
So the product, final product will be that.
Yeah, for what I've listed here, for excess I2 and OH minus, but if you wanted to isolate the carboxylic acid, then you would have to add a second step and add H plus to it.
So then the carboxylic acid should have been just a.
Oh yeah. This should have been actually an O minus.
Yeah.
This is after the word is workup. So we're gonna add H plus to it. It's like the Grignard reaction. When you do the Grignard reaction, they always show like the Grignard reagent and then the product, but really there's like step 1 is the addition of the Grignard, steps 2 is the workup, adding the H plus to it to get the product out. I should have probably said it, but I apologize. All right. Yeah, the next reaction. This is kind of a funny reaction. It's called a. Huh?
Can you do that with other halogens? The iodoform?
Yeah. So you can do chloroform, you can do bromoform, but iodoform is typically iodine is. If you had any, I don't know. There's not there. Suppose it would work. Yeah, but in general, it's called the haloform reaction. I don't know how well it works with fluorine. I imagine it works with fluorine. I've never seen that, but I've seen with chlorine, bromine, iodine. And then AT, acetane, that's like, there's so little actually known about it.
The only difference is the carbon byproducts.
Yeah. So if you wanted to make chloroform.
Oh, and we're going to do a mechanism of this, the repetition steps, do we have to include that?
No, just say lather, rinse, repeat. You know how when you wash your hair, they don't tell you put soap in your hand. They say you wash your hair, right? Get your hair wet, put soap in your hand, wash your hair. Then they say lather, rinse, repeat, which means take a little soap in your hand, put it in your hair, wash it. Yeah. You don't have to.
Yeah.
You never read the instructions on shampoo, huh? You never just like read the label of a shampoo bottle, say, what the heck am I putting on my head?
No, I just check if it's sponsored or not.
And then the more chemistry you get, you start reading it, and you go, well, that's interesting. I wonder why they added that.
I look at it, I just know.
All right, last reaction. I'll just outline it for you, and then I'll do the mechanism next time. But this is halogenation again. And then we'll talk about like, what do you do with all these products? Because once you get the halogenation down, you can make all kinds of stuff out of it. But halogenation of the alpha carbon of carboxylic acids. And man, I'm all of a sudden became dyslexic. Acids. Okay. Wow. So you can't straight up, like if you have the CH2 and then you have the C double bond O, OH, you can't just flat out pull this guy off because this is more acidic. It's called the hydrogen. Yeah. Well, that's essentially what you're going to end up doing. So it's more acidic than the alpha hydrogen. Okay. So the result is when you pull that off, the carboxylate, the C double bond O, O minus, right? This outcompetes. I'm running out of space on this. It outcompetes the alpha carbon for resonance stabilization. In other words, you can't stabilize the alpha anion anymore because the oxygen has a negative charge on it, and it donates electron density to this carbon much more efficiently than the anion here does. And so that, in essence, by taking this first hydrogen off, this pKa now is suddenly very, very high. So the same thing that we've done in previous chapter, we take the OH and we replace it with something that doesn't donate electron density well. And that's typically done with bromine. So the first step in this reaction is to form this. And the mechanism is actually a little bit more complicated, I think, than shown in your book, but I'll talk about it when we get there. We're going to make this. We're going to make the acyl halide, and bromine is chosen in particular because bromine doesn't donate electron density well because it's so much larger than carbon. Okay, so this is a poor electron donator. This is done using PBr3. And usually that's done by using phosphorus and bromine, like Br2. And once that's done, then you can be replaced now by Br. And so we'll go through that. We're basically out of time. I don't want to go into all of it. But you'll halogenate the alpha carbon, and then you'll get the carboxylic acid back by essentially adding water to it. It actually comes back through a kind of a complicated chain of reactions. But in essence, in the second step, you end up adding water, and you'll get your carboxylic acid back, and you'll have your bromine. Okay. All right. Well, that's all we have time for. That's it.
You're checking notebooks on Friday, right?
Yeah. So this week, you're going to give me your notebooks, and that's how I'm going to grade your spectroscopy stuff. Your spectra should all be in your notebook, and you should have drawn the structure of your three unknowns, and then written like major, information about them. All right, stopping the
Do you
recording.
want the lab report questions on the notebook as well, or just a summary?
Oh,